If you've studied AC electricity before, you've probably come across the root mean square voltage, or RMS voltage for short. In the UK national grid, this is 230 volts. What you may not know is why this number is so important. After all, at first glance, one might think the maximum voltage, which is square root 2 times larger than this, is a much more important number. But it's not. The UK national grid, and all national grids worldwide, are rated by the RMS voltage only. In this video, we'll see exactly why this quantity and the RMS current are so important when studying AC electricity. To do this, we'll take the following steps. First of all, we'll figure out how electric current behaves in a simple resistive AC circuit. From this, we'll learn how to calculate the power, for which there are two kinds, instantaneous and average. This will expose a rather annoying problem with AC power, which we'll use RMS values to fix. And in doing so, we'll see why this number is the one we use for national grids. So, let's start with the alternating voltage source we built in the previous video, which generates a sinusoidal voltage like this. To keep things simple, we'll replace all the generator parameters, i.e. the magnetic field, coil area, and angular frequency, with a single constant Vmax, which is just the maximum voltage in our AC cycle. So the voltage as a function of time is Vmax sine omega t. So what happens if we connect this to a simple resistive circuit like so? This is actually incredibly simple. A resistor doesn't care whether a voltage is AC or DC. Resistance is just a property of a material and its geometry, so it's completely unchanged by the type of voltage through it. At each instant in time, the circuit behaves exactly like a DC circuit with whatever voltage happens to be at that instant. So the current through the circuit is simply I equals V over R, and if we substitute our sinusoidal voltage in, we get the sinusoidal equation for the current. And this immediately tells us something very important. In a simple resistive AC circuit, the current is completely in phase with the voltage. All this means is that the oscillation of the current is perfectly in time with the oscillation of the voltage. And this matters a lot. But we'll explore that more in later videos in the series, when we make our circuit more interesting. For now, you can think about why this might matter as we calculate the next quantity that we care about, which is the power output. To calculate the power, we'll use our basic equation from DC circuits, which is P equals I times V. Substituting in our equations for voltage and current, we get the following power expression, which depends on sine squared of omega t. We can plot this graph like so, which lies completely in the positive y-axis, unlike the voltage or current. This makes complete sense, as if it wasn't, we'd be getting a negative power, which would mean we'd be gaining energy from the resistor, which is obviously ridiculous. Either way, unlike DC circuits, the power is not constant. It oscillates in time. We call this quantity the instantaneous power for this reason. The problem is that this instantaneous power isn't a particularly useful quantity on its own. What we really care about is the total energy delivered over time. This means we care about the average power, and this is different. To find the average power, we need to identify the average value on this power graph, which we can calculate with the following method. Let's consider one full repeating cycle, which takes exactly one time period t. To get the average value, we integrate the power equation from 0 to t, then divide through by t. Substituting in our power equation and moving the constants out to the front of the integral, we get this expression, which involves the integral of sine squared omega t. I won't show this full derivation here, so if you want to try and solve this yourself, feel free to pause the video. Upon evaluating this integral, which is a standard mathematical result, and multiplying by 1 over t, we get exactly 1/2. So the average power is Vmax squared over 2R. This result is completely correct, but it's awkward. When working with DC circuits, we're used to writing power as P equals V squared over R. But here, we've picked up an extra factor of 1/2, which makes AC power feel different and not very intuitive. It means we can't use our DC circuit equations, which would simplify things greatly. So instead of constantly carrying this factor around, we do something smarter. We define a new voltage, the root mean square voltage, or RMS voltage. This is simply the maximum voltage divided by square root 2. Why do we use this definition? Well, if we write the average power in terms of VRMS, the expression becomes VRMS squared over R, which gets rid of the factor of 2. This is of course identical to the DC formula. In the exact same way, we can define the RMS current as the maximum current over square root 2, which is equivalent to the maximum voltage over R times square root 2. And now we can write power in any of the familiar forms that we use in DC electronics. Why does this matter? Well, we can say that an AC voltage's RMS value is the DC voltage that would deliver the same average power to a resistor. And that's it. This is why we say the UK mains is 230 volts, the RMS value, rather than the peak value, which is around 325 volts. This AC supply delivers the same average power as a 230 volt DC supply. And because of this, any AC circuit made entirely of resistors can be analysed exactly like a DC circuit, as long as we use RMS values. We can use Ohm's law and all the power formulas. So let's summarise what we've learnt. In a purely resistive AC circuit, the voltage, current and power all oscillate. But the instantaneous power isn't particularly useful on its own. So we calculate the average power, which has the exact same formulas as the DC power, as long as we use the RMS voltage and current, which are just the maximum voltage and current divided by square root 2. Now this is all correct, but there is a catch. In a simple resistive circuit, the voltage, current and power all rise and fall together. And because of this, we can use the DC formulas for the average power. But this is a very special case. In most AC circuits, the current and voltage are not aligned. And when that happens, power behaves very differently, such that energy can actually flow back into the source. To deal with more complex AC circuits, involving things like inductors and capacitors, we need a better way of thinking about AC electricity. In the next video, we'll introduce phasors, a mathematical tool that encodes both magnitude and timing at once, turning complex, time-dependent AC into simple geometric problems. P.S. I'm currently updating my app to include worked problems and solutions for all the videos on my channel. I'm also going to make worked practice problem videos in the near future. Stay tuned and subscribe for more. Thanks for watching.